Hi everyone, Mr. Rowe here, just checking in with a quick video for 3.2 linear regression. I don't think this video will take very long. I was going through it. I was going to do like the hybrid half fill out, but the way it worked out, I just ended up filling out the whole thing. So I'll just kind of talk through it and we'll go from there. So just a couple key terms. What are we doing when we're doing regression? Well, you actually used to do it in grade 9 with your unit on scatter plots. It's when you would draw a line of best fit, and then you would use that line of best fit to make predictions. So here's the formal definition here, and you did this in a couple ways, by interpolation and extrapolation, if you remember from grade 9. If you're making a prediction within the given data, that's interpolation, and if you're making a prediction beyond the given data, that's extrapolation. We'll see an example of that when we do our example. Now, in grade 9, you would just look at the scatter plot and kind of eyeball your way in and draw what you felt was a line that was as close to as many points as possible, an equal amount on above and below the line, etc. However, now that we're in grade 12, there is a method it's called the least squares fit, which is going to give us the exact line of best fit given the two variable data. So this is how we do it. First, we'll define a residual. So basically, a residual is a vertical deviation of each data point from the line of best fit. So I've already drawn them in. So if this is a data point, then the residual is this vertical distance from the point to the line of best fit. So it wants us to draw the residuals for each data point, so I did there. So for a line of best fit, if you've drawn a perfect line of best fit for the data, the sum of these residuals should be 0. Because if they weren't, if this line of best fit was lower, then the positive residuals would be bigger net sum than the ones below the line. The sum of the squares of the residuals would also have the least possible value. So if I took all these distances, some are positive and some are negative, but I squared them and then added them up, the least squares line, the best line of best fit, that value would be the smallest. So how are we going to find this algebraically? Well, again, the reason why I wanted to do a video lesson is because I didn't want people to see this and get scared. But hopefully by now, we're getting used to these kinds of formulas and we're not overly intimidated by some of these symbols. So again, this is this Greek letter sigma coming up again, and that just means sum of. So in order to find the actual equation of the line of best fit, you should recognize this right here. This is the equation of a line, but instead of y equals mx plus b, which you saw in grade 9, now it's just y equals ax plus b, but the a just takes the value of m. It's the slope of the line, and b would be the y-intercept. So our goal in finding the equation of the line of best fit is finding the slope and finding the y-intercept, and we do that by using these two formulas. So the first one is a scary one looking here, where you take the sum of all x times y minus the sum of x times sum of y, divide that by n times the sum of all x squared minus the sum of all x squared. So there's a difference there, right? This is me taking all the x values and squaring them, then adding up those values, and this is me adding up all the x values and then squaring them. And then to get the y-intercept, you're going to do exactly what you did in grade 9. You basically rearrange this y equals mx plus b formula, and we're going to put in a value of a, which we just found, or in grade 9 you found m, and then x and y. And in grade 9 you used a point. Well, we don't have a point on our line, so we're going to use the average of x and the average of y, the mean x and mean y value. Sub those in, and we'll get the y-intercept of the line of best fit. So let's do an example. So this is a table that shows the data for full-time employees of a small company. So it gives you the x variable is age, and the y variable, the dependent variable, is their income. So I don't know why my graph, yours isn't cut off, but mine, every time I load it onto Smart Notebook, sometimes it cuts off these graphs, but I did my best to kind of fill in where I thought these were. But basically what you observe here is that as you get older, you're going to tend to make more income. So here's our scatter plot, and if this was in grade 9 and you were asked to classify the correlation, I would say this is a pretty strong positive linear correlation. As you can see, if I were to kind of do an eyeball line of best fit, like so, all these points are very tightly clustered around this line. If you wanted to verify that it was a strong positive linear correlation, you could do the R value, which we did in the last lesson, and that would probably give you a pretty high value close to 1. But that's not what we're doing today. We're not worried about the strength of the correlation. We want the line of best fit. Does the line of best fit look like this? Does it look more like this? What is the precise line of best fit? We'll use the least squares method. So here's a table with the data, and really all we need to use in order to fill out this formula is we need the x value squared and then x times y. So this value is just, you take the value of x, you square it, so 25 squared, 19 squared, and so on. This column here you get from multiplying each age with the income that goes with that age. So 25 times 31, 19 times 18, 44 times 52, etc. And then we just need all these sums. So down here, I have the sum of all the ages, the sum of x. I have the sum of all the incomes, this will be in thousands of dollars, the sum of y. Then I squared all the x's and added those up, and then I multiplied each age by the income, each x, y, and then added those up. So you have a formula, and lucky for you, you won't have to memorize this formula as kids would normally have to do. And we're going to plug in these values. So n is the number of data points, so there's 8. And then the sum of all x times y is 13,221. It's right there. The sum of x is 292. The sum of y is 329. Divide that by n, which is 8, times the sum of all the x squareds, which is 11,712, minus the sum of x, adding up x is 292. Then you square it. And when you calculate that, you get an a value of 1.15. This is the slope of your line of best fit. That's all this is. It doesn't tell you anything else other than this is a positive correlation, because it's a positive value, you know your line of best fit is going up. The slope of your line is positive. It doesn't tell you anything about the strength. You just know that the slope is 1.15. So now we need the y-intercept, b. So it's y bar, or the mean of y, minus a times x bar. So what are these again? This notation is an average. So what I did was I found the average income. So I added up all the y values and divided by 8. So 329 divided by 8. The average income was 41,125, or 41.125. Then I found the average for x, the average age. 292 divided by 8, the average age was 36.5. So when I put in the average y, the average income, minus the slope of the line, times the average x, you get a b value of negative 0.85. And this is simply the y-intercept. So if I were to go back to here, again, this, or wherever this graph is, just up here, again, it's cut off unfortunately, but wherever it is on yours, wherever that negative 0.85 would be the y-intercept, and then the slope would be 1.15. Probably be something very close to that. But instead of using our graph to do predictions, which may or may not be accurate depending on how you drew your line of best fit, we now have an equation for the line of best fit. So we're going to use our equation to make predictions. So we're going to predict the income for a 21-year-old and a 65-year-old. So if I have the equation y equals 1.15x minus 0.85, well, in this case, x is age. So if I put in age equals 21, it's going to be 1.15 times 21 minus 0.85. You get 23.3, which in the context of this question is $23,300. So just to show you that on the graph, and this is interpolation. So that would be something like this. So he's 21, so I think these go up by 5s. 5, 10, 15, 20. So 21, I guess I should have my line of best fit back. Maybe something like that, approximate. And then we'll go ahead and make this red. Go here. Okay, so the 21-year-old, 5, 10, 15, 20, 21. So it would be around here. Then you slide across, and you can see that's pretty close to the 23,000. But notice that this prediction is within the given data. That's why it's interpolation. The first data point is right here. And the last data point is out here. So any prediction you make within these two arrows is interpolation. Anything outside of those arrows is extrapolation, which is what happens in the next question. It wants the 65-year-old. So I plugged in x equals 65, and I got approximately 74,000 or 73,900. And this is going to be kind of off our graph, but as you see, 5, 10, 15, 20, 25, 30, 50. Yeah, it's going to be off our graph, but it would have been, maybe we'll go green for this one. It would have been something like this. Line, green, dotted. It's way off our graph, so it's not even going to work. But it would have hit the line over here and then come across over here. But this line would have been much further out over here. But what I was trying to illustrate with this is that this prediction was made beyond this point. It didn't really work because I can't get this line out far enough. So now this equation works both ways. We have two variables. We have age and income. So if I give you the income, you could also sub that in, do some algebra, and calculate the age. So if I put in income equals 60,000, which corresponds to y equals 60, I can put that into the equation and also solve for x. So I've gone ahead and done that. Negative 0.85, bring that over, becomes a plus. Isolate x, and you get 52.9, or about 53 years of age. So really that's all you're responsible for this lesson. Normally we would take this a step further and get onto the computers, and I would show you how to do these kinds of calculations using Fathom, and then we're also going to use technology to investigate some outliers, but you'll do that with one of your homework questions where you'll just do it manually. But of course, we're not in the classroom, so that won't be happening. So again, this is optional. You can always, if you have the initiative to somehow get Fathom on your computer, maybe there's a free version somewhere you can find, you can try all these investigations on your own. Other than that, you can attempt the homework that's down here, and we'll go from there. So take care.